In this second part of the video, dedicated to the mixture of gases, we see the case of a mixture between gas and steam. As usual, we will display some theory and an application with real numbers. Let's start. What about the mixtures of gas and vapor? There is a difference between the mixtures of gases and the mixtures of gas and vapors, because in this case there is condensation or evaporation and the mass in the gaseous phase can change. The two fluids must be treated independently by different equations. The thermodynamic state is described by 4 instead of 3 variables if we deal with two fluids. There is one extensive variable needed, either the total volume or the total mass, then two intensive variables, for instance pressure and temperature, and one mass ratio, m1 over m2, where m1 is the mass of the gas and m2 the mass of vapor. They exist following relations. The temperature of the gas and the temperature of the vapor are the same. The total volume of the gas and the total volume of the vapor are the same. The pressure of the gas plus the pressure of the vapor equals the total pressure. The mass of the gas plus the mass of the vapor equals the total mass. This mass is constant, but not the gaseous mass, because there is a condensation or evaporation, as we have said already. The enthalpy of the mixture is the pounded average of the enthalpies of the two fluids, where the pounds are the masses. The enthalpy for the gas is a function of the temperature, and the enthalpy for the vapor is a function of temperature, pressure, and or the steam quality, and similar relations can be found for the internal energy and the entropy. We remember that in the superheated region, enthalpy as well as internal energy and entropy is a function of temperature and pressure, while in the saturated region is a function of temperature and steam quality or pressure and steam quality. We do an example that is a mixture of steam and air. Steam is a fluid A and air is the fluid B. Starting conditions are volume 1 cubic meter, temperature 120 degrees, pressure 300 kilopascal, and the ratio between the masses of the two fluids is 5. We have given 4 parameters. The two fluids will be treated independently as two different models. Fluid A, a real gas, fluid B, an ideal gas, but they interact together in the transformations. The transformation A is isochoric from 1 to 2. The temperature 2 is 170 degrees. The transformation B is isentropic from 2 to 3, where the pressure 3 is the same as pressure 1, 300 kilopascal. The transformation C is isobaric, 3, 1. Let's find now the parameters of the fluids. For the fluid A, the steam, the molecular weight is 18.016. For the air, the molecular weight is 28.96. Ra is 461.5, Rb 287.1. For air, we consider as ideal gas, we know the Cp, we calculate Cv as Cp minus R, and we calculate K as the ratio between Cp and Cv. The values are displayed here. We look now for the partial pressures of the state 1. The pressure of the fluid A, the steam, is a function of the temperature assuming saturated conditions. For 120 degrees, this value is 198.7 kilopascal. The pressure of the air is the total pressure minus the pressure of the steam, therefore 300 minus 198.7, 101.3 kilopascal. Let's look for the mass of the fluids. The mass of the vapor is found using the state equation, where Z is the compressibility factor for being a real gas and is given for the temperature of 120 degrees. In this case, we consider for the pressure the value we have found in the previous slide, and for the volume the total volume, neglecting the volume of the liquid fraction. Later on, we will confirm this assumption. The mass of the air is found using the state equation, and we get 0.898 kg. Now we use the information that is given, the ratio between the masses of the two fluids. It is 5, but the mass of the steam is the sum of the vapor mass and the liquid mass, and since we know the mass of the vapor, we find the mass of the liquid, that is 3.368 kg. The total mass of the steam is therefore 4.491 kg, and the mass of the steam plus the air is 5.389 kg. The steam quality is, for definition, the vapor mass fraction, and for the state 1 we find 24%. Let's write all the thermodynamic variables of the two fluids for the state 1 in a table. We notice that the liquid density of the steam is in the range of 1000 kg per cubic meter. Therefore, the quantity found has a volume of about 0.3% with respect to the total volume and can be neglected. For steam, we can calculate all parameters with the application Thermonator or a similar one. For air, we use the equation of the perfect gases, and the entropy is calculated with one of the formulas 25, 26 or 27 seen in the lesson 3. We remember that in the saturation region, the specific volume of the steam is given by the steam quality times the specific volume of the steam plus 1 minus steam quality into specific volume of the liquid, and similarly for entropy, internal energy and enthalpy. For the mix, we consider P equals PA plus PB, S equals MA into SA plus MB into SB, where S is capital S divided by M. S is the specific entropy. Important notice: the thermodynamic cycle of each fluid is different from the cycle of the mixture. Even though the transformation 1,2 is isochoric for both the mixture and the single fluids, the transformations 2,3 is not isochoric for the single fluids, as well as the transformation 3,1 is not isobaric for the single fluids. We calculate now the state 2 after the isochoric transformation. From the known temperature T2 170 degrees, we calculate the pressure 2A, that is a function of the temperature, the pressure 2B with the state equation, we find 113.7 kilopascal. The pressure 2 is the sum of the pressure 2A and the pressure 2B, we find 905.8 kilopascal. Moreover, the volume of the vapor and the volume of the liquid are also function of temperature and can be calculated for the fluid A. For air, from the temperature T2 and the pressure P2B, all other variables can be calculated. From the volume conservation, we know that V2A is equal to V1A, which has been calculated already, 0.22, and since we know all the other parameters, we can calculate the steam quality X2. We find 92%. With the steam quality, it is now possible to calculate the remaining variables entropy, internal energy, and enthalpy with similar formulas. Let's calculate now the state 3 after the isentropic transformation. This time we do not know the temperature T3, but only the total pressure P3 that is equal to P1. Moreover, we know that the mixture entropy does not change. Therefore, capital S3 equals capital S2. To solve the state, we need 4 variables. 2 are known, pressure and entropy. 2 are unknown. We choose, beside T3, the steam quality X3, assuming to be still in the saturated region. The solving procedure is as follows. Given T3 and X3, we calculate the specific volume of the state 3 for the steam, then the total volume as the product of specific volume and the mass of the steam, then the specific volume of the air, dividing the volume by the mass of the air, and the pressure of the air from the state equation. The specific entropy of the air is a function of temperature and pressure. We can calculate using one of the formulas already mentioned for the ideal gases, and we can calculate, moreover, the partial pressure of the steam that is a function of the temperature. Moreover, we calculate the specific entropy of the steam because we know both temperature and the steam quality. And finally, we need to satisfy 2 equations. The first equation says that the sum of the partial pressures is equal to P3, which is given 300 kilopascal, and the second equation says that the total entropy, capital S3, is equal to the entropy of the state 2, which is also known. T3 and X3 are found till when those conditions are satisfied. We can use, for instance, the Excel solver. All the states are then collected in the table aside. We finish now with the calculation of the cycle. What is the work and what is the efficiency? For the transformation A isochoric from 1 to 2, the heat is the difference of the internal energy, that is the sum of the difference of the specific internal energy for the gas A into the mass and the difference of the specific internal energy of the gas B into the mass, we find 6,410 kJ. The work is the product of the volume and the difference of the pressures. We find 609 kJ. Delta H, differential enthalpy, is the sum of Q and technical work, 7,018 kJ. For the transformation B from the state 2 to the state 3, the transformation is isentropic, so the heat is 0. The technical work equals the differential enthalpy, and the differential enthalpy we can find with this formula, where we have 2 parts. One is the gas A and one is the gas B. Negative 940 kJ. For the transformation C, isobaric from 3 to 1, the heat is a differential enthalpy for definition. The technical work is 0, and the differential enthalpy has similar expression already seen above, with of course the different states. Negative 6078 kJ. The work of the cycle is the sum of the works of the transformations A and B, because for the transformation C is 0, and we find negative 332 kJ. The positive heat is only the heat of the transformation A, and we find 5.2%. We will see in the next video the completion of the chapter 5. See you, bye bye.